So, welcome to lecture number 6, probability statistics. We still have some people coming, which is good. I guess as the Christmas break is getting closer, I will see less people, but let's see how it goes. So thank you for being here again. Thank you for being so early, so that's nice. So today we have random variables and continuous probability density. So this is going to be, I think, the last lecture on distributions. And we move from what we have seen before, that is discrete probability distribution, to continuous probability distribution. So, because that is usually what you will see in the next lectures. So, we're going to talk about, like I said, from the discrete to the continuous, in the sense of we're going to learn about the cumulative density function. We have kind of briefly introduced that, but we'll do it more formally today. And then some rules, and of course, expected value, variance, and standard deviation for the continuous domain. And then our famous Gaussian distribution in the continuous domain. And then we will see the family of the gamma, including the exponential distribution. And finally, the last one will be the bipolar distribution. So let's see how it looks like. So, like I said, so far we have seen only discrete, right? Distribution, where we have actually beams that kind of form the distribution. And now we can go more to define this for infinite number of beams, if you want to put it some way. And again, we will have a random variable, a random x, right? And this function will map, x will map from the omega to the real numbers, right? And it will be bounded between 0 and 1. So it's the same thing as always. And then if you have such a function, f, that it bounds between 0 and 1, we can call it strictly like that cumulative density function, which is defined as the probability to this variable to take some values below or equal to an x value. Okay? This is just pure definition, but let's see how it looks like. So let's say that we have now x is continuous, so you can take any value, right? Infinite number of values right here, and between minus infinite and infinite, right? You can take any value. So this cumulative density function, it will be defined as the integral of our what is called the probability density function, what we will have seen before, between minus infinite and x. Okay? And what that means? So what we have seen so far is something like the top graph, right? Where we have f is our probability density function, it's the probability of the event to happen, right? For all the values of x that we can have. Now it's in the continuous domain, so it's a line, it's not beams, right? It's not discrete. So if you take the integral of this, and I hate this guy here, if you take the integral of this, then you get what is called the cumulative density function, which is basically if you will start from the very low part of the very low stream of the distribution, you start summing up the probability, you will start getting this, right? So it's accumulation of probability, right? And the area, all this area below here, has to be equal to 1 if you sum all together, right? Because that's pure definition of probability. And that helps us because portion of this will give us what is the probability to be less than a certain value x, for example, if you look in this direction, or larger than this value x. Okay? So the cumulative density function is something that we have seen in the Gaussian distribution last week a little bit, how we use that in the table. So, how you do the cumulative density function for the discrete domain? First, one notation in the discrete domain, the probability density function, sometimes called the probability mass function. I don't really like this. I don't know what mass has to do with this, but I would call it probability density function for both cases, okay? But in the literature, sometimes they call it mass function. And basically, it's what we have seen here before. So, for example, this is the case of the dice, right? So the probability of getting a 1, a 2, a 3, or 4, or 5, 6 is always 1 over 6. And here it will be any, I don't know, random variable. The probability to get a 1 is 0.2, the probability to get a 3 is 0.5, and so on and so forth, right? And then how you do the cumulative density function in the discrete domain, so instead of doing the integral, you are doing the summation, right, as always, yeah, the summatory. So first you start from the very left part, and then for 1, here's 1, until 1 there is 0, right, there is 0 probability. When you get very close to 1, it's still 0. But as soon as you get into 1, it becomes 0.2, okay? And this is what we mark it here. So the circle that is not filled is when you are infinitely closer to 1, okay? So it's 0. And then you jump immediately to when you get a 1, the probability is 0.2, okay? And then you mark this as a filled dot. That's the way to identify that you are actually jumping on. Then you maintain constant, right? Because there is nothing between 1 and 3. And again, as you are getting closer to 3, in the very last tiny piece of the 2.9999999, you get a circle that is not filled. And then immediately as you get 3, you jump again to 0.5 plus 0.2, so 0.7. Okay? And then you maintain constant until you get here again, and then you jump again, and you get 1, right? Because it's 0.37 plus 0.3, you get a 1. And that is the cumulative density function for this probability density function. And then if you do that, you can do the same for the die, and you will see that it's actually a straight line. So it's kind of a, you can imagine that this is an integral, right? The cumulative density function in some way has to integrate. And then if you have a flat, you should have a line. If you have a line, you should have a curve, right? It's a sort of thing. You can already imagine the shape of the cumulative density function from the probability density function. And then for the continuous domain, then you have, you can do a proper integration, so you don't do a summation because it's in the continuous domain. And I think I can, I don't know if this guy, yeah, I think I can sum here. So you can see here, so there are 4, let's say, normally distributed probability density function, and 3 of them are centered in 0, so you have a mean of 0, and the other have a mean around -2, and they have different variance, right? So that's what you can see here. And then if you take the integral of any of them, let's say the blue one, you start to accumulate until you start to decrease. So that's what you see here. It goes up and then it starts to slowly, it cannot go up too longer until you reach 0 again and saturate, let's say, on the top. And you can see that if you have the same mean, then all of them will cross in the mean, right? And of course, the mean that is skewed to the left will move the whole curve to the left, and different variance will give you different slopes. Okay, so nothing really crazy here, but this is pure function integration. So probability density function is the probability of the event to happen. Cumulative density function is the integral of that function. It has some properties. One I already said. It has to be, so for any probability density function, fx that is larger than 0, then this probability density function has to be the derivative, that's what I was saying, of the probability, the cumulative probability density function. And that's because the cumulative density function is integral, right? So the probability density function has to be the derivative, or has to have a derivative at f. And then our cumulative density function is always monotonically increasing, okay? Because you are accumulating, so it has to increase. It can never go down, right? Why it cannot never go down? Because it can never decrease, and that is because you don't have negative probabilities. Okay, so you always some positive values. And then, of course, like I said, the area under the cumulative density function has to be, the area under the area about, below the probability density function is 1, and the cumulative density function is also 1. For the continuous part, you can imagine that it's not that we did it with the discrete values, that we have a beam, right? And we say, what is the probability of x equal to a value? Here you have interval because you have infinite number of values, right? So you're always going to evaluate intervals. They can be as small as dx, okay? So you're always going to have the probability within an interval of the event to happen. And then let's say that you have some values d that is larger than a, then you can define the probability, the cumulative density function between these two values a and b. So what is the probability of x to be between a and b? And that is basically the subtraction of the probability density function in b minus the probability density cumulative density function, sorry, on a. And like we say, we have to integrate our density function, right, in a between minus infinite and b, and between minus infinite and a. And that's basically what we are doing here. So we are calculating the area under the curve for this interval that we have here. And by distribution of integral here will be the integration of the probability density function between a and b. That's basically graphically what you're seeing here. All right, so we're gonna be doing this, but no worries, it's nothing really crazy here. So, in the case of the continuous, we can also define the expected value, the variance, and the standard deviation. The only difference is this was a discrete case. What is the difference? That we now have an integral instead of a summation, right? Because in the continuous domain, we have to do it over all dx, right? And again, it has to be, the expected value has to be less than infinite. For the variance, we have before a summation, right, for all the values. Now we will have integration again. So the integral between minus infinite and infinite of each of the realization minus the mean of the average squared times the probability density function, right? So there is no probability function here as we have it here, but the density function. And then if you take the square root of the variance, you get standard deviation. And as before, x can be also a function gx, and we will have the same property. So this is exactly the same as before, but for the continuous case. So let's have an example solve. How we go from the probability density function to the continuous density function. And this will be hopefully a refresh or maybe a boring slide on how to integrate signals. So let's say that we have a probability density function that is defined as 0.02 times x, so a linear relationship, and that this value is only defined between 0 and 10. Okay? So this is what you see here. So below 0 there is nothing, above 10 there is nothing, and in between is a straight line with a slope of 0.02. Okay? Nothing difficult. So how we calculate the cumulative density function? Well, we integrate this function over minus infinite and x, right? Minus infinite in this case will reduce to 0 because after 0 there is nothing, and x will go to x, right? So how we integrate the signal? Remember, we can take the constant out of the integration, and then we'll have the integral of the variable between 0 and x, right? And that is, remember, 1.5 of the variable squared, and that is because if you take the derivative, at least this is the trick that I remember, you take down the 2, so the 2 over 2 will be 1, and then you will get u at the end, okay? So you have to remember to reverse that order, and then this is the integral that you get, and then you have to evaluate this integral between 0 and x. For 0 is 0, so only get x. So our cumulative density function is 0.01 times x squared. And this is what you see here. X is only valued between 0 and 10. So below 0 is 0. Up to 10 is actually a square, it's a quadratic curve. Okay? And that's what I was saying. Remember, flat line is a slope. First order is a second order is a third order, and so on and so forth. What can I tell? I think are all engineers or something like that. So you should know this. Good. All right. So how we have the Gaussian distribution on our continuous domain is pretty much the same. We have seen this slightly last week. Remember, this was our function of the Gaussian. We have some exponential, remember, and we have some constant that define how flat and how steep the belt shape was. And then if you take the integral of that, you will get your cumulative density function for the Gaussian distribution. And there is nothing that has integrated the exponential part because the constant part can go out. And like we saw this, there is a standard version of the Gaussian distribution, as we can get a standard version of anything by just applying our linear transformation, right? The standardized, we get the standardized normal distribution that was just subtracting the mean and divided by standard deviation. We saw that last week, right? And that gave us a distribution that had mean 0 and a standard deviation of 1. And the good thing of this was that we can get a table now, because this is a standard distribution, so it can be tabulated because it would be the same for all our calculations. And then you can use that table for solving your problems, right? And now it becomes the phi function, right? When it's standardized, remember? And that was and then to get this would be our CDF, our PDF. And then to get our cumulative density function, you have to integrate phi, okay? And that is usually what you have in the table. Usually you have the cumulative density function of the Gaussian distribution. That's what you usually use for getting your probabilities for solving your problem. If you remember, we can approximate any probability of x be smaller or equal to some value as the phi function and standardize it, right? We already saw that. And since it was, since it's mirror symmetric, right? We can get that the phi function evaluated in the negative of z is equal to 1 minus the, well, this is because of the distribution, sorry, because of the definition of probability, but this is because of mirror symmetry. If the value is between minus z and z, it can be equal to just 2 times the function evaluated in z minus 1. Okay, this is something that we already have explored. So we can just get the 2 tails or 1 tail, and that is enough information. So, okay, so we have seen this before, but let's now put it in the framework of continuous distributions. And again, an example that is closer to what we saw last week. I have it now earlier in the morning. The last time was at the end of the class, so maybe you already forgot what you have seen that time. But let's say that we again have a device that we produce, right? And that have an approximated normal distribution, right? They have a scale, right? Let's say that it's a scale and measure weight, right? And if you have error, because any scale will have error, and we assume that it's normal distributed this error, and that the mean will be 0, right? That's good. And I will have a standard deviation of 0.45 milligrams. So depending on what your accuracy or precision you want to have, this is more or less okay. Okay? So now we want to calculate what is the probability that our error that we're going to have is less or equal to 0.45 and 0.9 milligrams. Okay? And we'll see why we choose these numbers. Let's see. So every time you talk about normal distribution, usually you present it in this way. This may be not new for you. So you have n means normal distributed with mean whatever and standard variance whatever. In our case, mean is 0 and our variance is 0.2025 because it's this guy squared. Okay? So that is what we have and what we know. Let's calculate the probability. So remember, we can use our phi function, right? Which would be the cumulative density function, right? Between A and B, right? And that is also can be, again, the minus set can be, if we take into account that the minus set, but the phi function evaluated minus set is equal to 1 minus the phi function evaluated set, we can come here and say, we want to have an error that is, what is the probability of error to be less than 0.45, right? Plus or minus, can go the error in both directions. So we take the absolute value, right? So it's the same as saying what is the probability x between minus 0.45 and 0.45, right? Then we can do what we do always, that is standardized, so we can use our tables, right? So we subtract the mean and we divide by the standard deviation in both the streams and also our variable, right? Then our mean is 0 and standard deviation 0.45, okay? And then what we get? We get that what is the probability of our standard variable to be between minus 1 and 1, okay? Right? And then we can apply this, right? So 1 minus 1, the phi function evaluated in 1 minus the phi function evaluated in minus 1 is equal to 2 times the phi function evaluated in 1 minus 1. So we only have to find the phi function evaluated in 1, okay? And if we go to the table, it's 0.8413. You plug the number, and what you get? You get 0.68%. And if you remember, what are the probabilities in the standard normalized Gaussian distribution? We saw this. One standard deviation gives us around 68% of our probability. Okay? So every time you go to 1, you will have 68%. Okay? So that's why we choose 0.45 in this case. Let's say what happened if you have 0.9, right, to be less or equal to 0.9 in both directions. Again, you have to normalize everything, your variable and the limit. You do this, and now you have between 2 and minus 2. And then if you go to 2 in the table, we do the same process, you will get 97%. So 0.77, right? So 2 standard deviation will be around 98% of the probability, okay? And if you go to 3 standard deviation, you get already 99%, right? These are the 3 numbers that you always relate in your Gaussian distribution: 68, one standard deviation, 2 standard deviation, 98, 3 standard deviation, 99. Okay? So that's for you to verify that this actually is true. All right. So then we get we have defined continuous distributions. We have defined cumulative density function formally. We have see how this applies to the Gaussian distribution. Now we go to the exponential distribution, which is something related to Poisson distribution. Because if you remember, it was something that when you have a low probability of the event to happen and you have a large n, right? And you have a binomial, in this case was a binomial model. Now, the continuous version, let's say, of the Poisson distribution will be the exponential distribution. And we'll see that this is a special case of the gamma distribution that we will see in a few minutes. Okay? So, again, some motivation for this exponential distribution is for individual events that have rarely happened. Okay? So it could be, I don't know, the chances of, no, I don't want to do that check. So the chances of Argentina to win NBA game, I don't know, whatever, like a basketball game. I wanted to say something else, but I didn't want to hurt any feelings. So they have the proportionality is that the longer you wait, right, the more chances you have to to see the event, okay? The homogeneity that it can happen to, for all of the events have the same chances to happen, and then the one event is independent to the event that happened before, okay? So these are weird things. So typical examples before my, beyond my back shock that I say, are, for example, meteorite impact. So the chances that we have a meteorite to come to Earth is very low, but it could happen. Hopefully, the failure of an electronic component that you're fabricating have a low chance to happen, and you probably will have to wait until this happens. And our famous radioactive decay from physics example. So the exponential distribution is like in the case of Poisson, parameterized by lambda. Again, in lambda, this lambda has to be larger than 0, and the probability density function of exponential distribution is given by this formula, which is just this lambda times the exponential function to the minus lambda times x, and x is our value. Okay, so you can already have a feeling that lambda shapes the distribution, right? It's the parameter that you give the shape. And then if you take the integral of this, you get your cumulative density function, which is 1 minus exponential to the minus lambda x. All right, nothing crazy. For x larger than 0, that is also. If not, it's 0. So here you get the respective value for the exponential density exponential distribution 1 over lambda, and then our variance is 1 over lambda squared, and the standard deviation square root of that. And you can see here the shape. That's what I wanted to say. You can see for different values of lambda. The smaller the lambda is, the distribution will start in or intercept the distribution with the y-axis is lower, and the decay is slower. Okay, which makes sense because here, so the larger is lambda, more decay you will have because it's in the negative exponent, and the larger lambda, the amplitude at the beginning has to be large. So nothing pretty crazy here. And that's what I was saying. Basically, that is. Some cases are that are using exponential distribution, and I can think about an engineer example, which is a capacitor, right? The charging and the discharging of the capacitor is something that you could think, and they have a similar equation to this, but you have charge and voltage, right? But you could think about life expectancy of a device, the T, famous T, and that would be that will be defined by this formula, and it's exponentially distributed. So one thing here is interesting is, let's say that we want to calculate. So this is to picture better this idea of the probability of an event to rarely happen, and that it could happen at any time, and it have always the same probability to happen. You can say, what would be the probability of an event T, or life expectancy of T, to be larger, so the T is the time of this to failure, right? So let's say that, what is the probability of a device to failure T in a time larger than T plus H, given that already we have seen a time of T. So time small t has passed away. What is the probability that the event will happen at T plus H? Okay, in a longer time, right? So we can say that by, remember that this is a conditional probability, so we do the intersection over the reduced space, right? So the probability of T to be larger than T smaller or T lowercase plus H intersected with T larger than lowercase t. No, very nice letters. So T larger than T plus H, it already includes T larger than T. Okay, So we can really simplify directly by probability of t larger than t plus h. And we divide by that. And then if we plug our exponential cumulative density function here, we get lambda and lambda are cancelled, and then you get only a ratio of exponential. And if you get a ratio of exponential, you can actually sum up the exponent, right? And then you get exponential to the minus lambda h, which is nothing but the probability t to be larger than h. So what it means basically is it doesn't matter how long you wait. If you wait less or more, the probability is always the same that the event to happen. That's all that we want to say. Yes?
Regarding the exponential distribution function, you mentioned that when x is less than 0, the result is 0.
Yes.
However, by substituting the equation, it won't be 0.
So, sorry?
When we substitute in the equation,
yes,
the exponential distribution function,
yes,
the result will not be 0. So, is it a type of approximation or something?
So when you substitute in which equation? Here?
The slide before the last one.
Here? So that's what I say. Yeah, so before that, it's not defined. That's all. It's lambda and then it's 0. So a 0 would be lambda and then it's 0. Or yes, it would be lambda because this will become 1.
Exactly.
And then it's lambda and then it's not defined. No problem. Okay, so this was just a back show that if you're really waiting for the event to happen, so the code to happen, and then at some point this spontaneously at t to h you really crash and you're really not coming out. So because this term is called, this proof that we have here is called spontaneously, right? Whatever. So that's called. What I was saying with this is that it's the memoryless property of the exponential distribution, or that the event or the phenomenon would happen spontaneously. All right, so let's do an example as always. So let's say that we are interested in knowing the life expectancy of an electronic component. This is very engineered example. And so we know that t is exponentially distributed, and then we have our density function defined like this. So at 0 is below 0 is 0, as we were saying. After 0 or equal to 0 is our exponential distribution, right? We don't know c because we don't know anything about. So we have to find out c or lambda. Or no, it's not a lambda, it's a c. And then we want you to know these two questions. What does the distribution function look like, right? Because of our particular case here of the electronic component, x. And once we have the cumulative density function, right? What is the number of elements that will survive at some t equal to 0 to 10? This is a typical thing. So you have a device, you fabricate it. And at some point you want to know what is the life expectancy of this device, and for that you have to calculate the distribution of this particular device because you have particular things that will fail. And you will like to know, for example, a light bulb, right? Or LED now bulb, right? You have, let's say, 10,000 hours, and then it will break. So that is the life expectancy of that bulb, right? So let's think about that. So first we have to find our function, and we know that the cumulative density function is always the integral of the probability density function. We know the function here, right? So we have to integrate, and again, by integration, you have to come down, when you do the derivative, you have to come down the 0.01, sorry, and then you have to have a 10 here in order to compensate for that. And then this is the integral of this function here, and you have to evaluate it between 0 and infinite. In infinite is 0, right? And in 0 is just is 10. So 10 times c has to be equal to 1, because the integral over the whole range of the cumulative density function has to give us 1. This is the area, right? Area. So if it's equal to 1, then you can get our c. Good. Now we have our C. Now we know our true probability density function for a particular case, right? And now we have to integrate it again. Now we know C. So now we have to integrate this guy, right? And that's what we do. We integrate it again, but now we replace C by 0.1 and nothing else. We do the same thing here, right? And if you do the calculation here and you evaluate it between 0 and 10, you get that our cumulative density function is 1 minus exponential to the minus 0.1 times t. Okay? Alright, so we have now a cumulative density function. It looks like this. You can see that it's an exponential. The other is kind of a logarithm, right? It kind of makes sense. And again, it's defining only for values larger than 0. And now we have everything to calculate what is the probability of the probability of event to failure at time t equal to 10. Okay? And that is nothing that says the probability of t to be larger or equal to 10. Okay? So we are interested in our probability density function to be larger than t. Okay? But as always, since this is now a continuous distribution, this will go to infinite, right? So we don't want to calculate it from 10 to infinite. It's better to calculate from 0 to 10 and then do 1 minus that, right? As always, the trick. Okay? And if you do that, you have to evaluate our cumulative density function in 10 and minus infinite, which in this case would be 0, because the exponential distribution is not defining or is 0 below 0. So that's what we do here. And then we just get 1 minus the cumulative density function at 10, and we just use our formula that we have calculated before, and we evaluate it in 10, and then we get 36.8 percentage of chances of device not being working at time t equal to 10. Whatever t equal to 10 means, could be 10 hours, 8 years, millenniums, I don't know, whatever. Okay? Good. Alright, so continuous distribution, cumulative density function, continuous Gaussian distribution, continuous exponential, well, it's defined only in the continuous, but it was a version of continuous version of the Poisson distribution if you want. Now we come to the gamma. And the gamma is a particular one because it includes the gamma. From the gamma you can deduct many other distributions, right? And especially you can define the exponential distribution from gamma. So gamma have two parameters. Exponential have only one lambda. Gamma is parameterized by alpha and beta. All these letters that at some point you will forget in your life, but at least one time you see it, and one time in your life you know that a gamma function exists. And then when some people say, oh yeah, it's gamma to, oh yeah, it's gamma to alpha, gamma, beta, you don't remember anything, but you say, oh yeah, alpha and beta, right? At least you have in your life. So one important function of the gamma distribution is the gamma function, right? So, which is defined as the factorial of x minus 1. That's the gamma function. And our gamma distribution, the probability density function, is defined by this nice formula here, that as always, it looks really elegant, but to come up with this beautiful equation, you have to be a genius as always, and good for us that there is many of them still alive. So is beta to the alpha divided by the gamma function evaluated in alpha times our random variable to the alpha minus 1 times the exponential to the minus beta times our random variable. That's it. It's only divided by positive alpha and beta. And yeah, and that's pretty much it. Yes, that is the formula. Yeah, this is just to, what is the difference between x factorial and x minus 1 factorial? It's just the same curve shifted to the right. Nothing important. So, when I say that we can define different distribution from the gamma, let's see how they look like. So, if alpha is equal to 1 and beta is equal to lambda, you can already imagine what kind of distribution could be. But let's do the example. So alpha is 1, so it will be beta to the 1. And then here alpha is 1, so this is 1, because it's alpha minus 1, right? 1 minus 1 is 0. So x to the 0 is 1. And then beta is gamma. Beta is alpha, sorry. Beta is lambda. And this guy is a factorial of 1, x, that was x minus 1 factorial, right? If alpha is 1, then it's 0 factorial, which means that this is 1. So we get lambda times the exponential to the beta is lambda to the minus lambda x. And this is the exponential distribution, right? So the exponential distribution is a particular case of the gamma distribution when alpha is equal to 1 and beta is equal to lambda. Then when alpha is equal to n, you get something that you don't have to remember, Erlang distribution. I don't know. Don't worry about that. You don't need to remember, just it's for anecdotal cases. If alpha is equal to some parameter divided by 2, you get something that we will see later, the chi-square distribution. We leave it for later. And if alpha is very large, then go to the infinite, not to the infinite, but very large, this guy becomes the normal distribution. Okay? So from the gamma, you can derive at least 4 distributions. Yes?
For determining the denominator, this is gamma alpha, right?
Again, sorry?
Determine the denominator of this equation.
Yes. Here. This guy?
Yeah.
Yes.
It has an, I noticed an equation in the previous slide,
Yes.
which I didn't understand. Like it wasn't the x minus 1 factorial.
This guy.
Yeah.
Yeah, but in this case is because this guy it cannot be approximated with a gamma distribution with gamma function is done. This is what we are defining here. And for this guy, this is for the cumulative density function. Sorry, this is integral of our. This is not nicely written here. It's a probability density function to the left, cumulative density function to the right. Okay. Sorry, I have to change the name on it. It's confusing. All right. So how will the gamma distribution look like? Actually, I'm happy that some people are really awake. So how the gamma distribution look like is like this. Again, I think I can zoom in. So different parameters for alpha and beta will give a different shape. You can see that it kind of approximates the, so it looks really like an exponential distribution for alpha that are equal to 1, right? That's what we were saying. And will be for different lambdas. If beta is lambda, right? And alpha is 1, you see that the orange and the blue looks really like an exponential. And then it will be shaped in other ways. So, and this is the on the right you have the cumulative density function and basic S integration. And depending on how the shape is of the probability density function or cumulative will look always as an integral of that, right? If it's exponential, usually tend to be like logarithmic. All right. So some difference between Europe and the USA, and this is just because you might go to the US or might read a book from the US, and there is a few the way that we use and they use, or they use and we use, is different. That we just call alpha and beta. And for some reason they call beta 1 over beta, so they reverse that. I don't know why, but it has to maybe with using inch instead of meters and things like that. I don't know if the British use that also, I have no idea. but then the function will look different. Just that if you go to Wikipedia or any website, maybe they look like this, the gamma distribution, and not like I have defined. That's just a note for you. And then, of course, the expected value will be different. One is going to be alpha over beta, and the other will be alpha times beta. Of course, we're in Europe, at least so long, so we would use always the Europe definitions, okay? So that's what I plan in the European Union thing here. And then we get our effective value variance for our distribution. There is a point of inflection and some value that you can calculate. You're free to do it. And some other characteristic of the gamma distribution, which I just put it here for your information. All right, so the last distribution of today, and the last few slides of today, is a Bible distribution. And these are useful distribution. It's not so common, Bible. It comes from Mr. Bible. And this is something that you can use, for example, when you're testing the strength of a material, for example, and you want to know what is the breaking point of that material. So you start stretching with a machine that measures the force, then at some point will break. And then you have to mark force equal to something. Then you do the same many times, and then usually it's why we distribute this kind of thing. And the only thing that you have to do from the gamma from the exponential distribution is to call x, you call it y to the 1 over alpha. It's just changing the variable that will change from exponential to Bible distribution, okay? And there is nothing else, that's all. So if you take the probability of an event to happen less or equal to some value, then you change x by 1 to the 1 over alpha, and then that's the same that passing alpha to the right in this inequality, right? No, I don't have to say that, I can continue to say that. It's like multiplying, on the both sides, and you get alpha. And then if it's we say that it's just as valuing the exponential distribution, this new variable, then this is our Bible distribution now. It's one for the cumulative density function, right? Yes, for the cumulative density, the probability density function. Sorry. So we will have 1 minus e exponential to the minus alpha to x to times lambda times x to the alpha. And again, as the exponential distribution is 0, we don't 0, and after that is the function value, right? And this is our yeah, exactly. This was the CDF, and by differentiation you can get our PDF, right? We go all the other way around. And that is our now probability density function, and it's defined as the formula that you see here. Of course, you're not going to remember this in your life. I have to see it again every time I do the lecture. So, but it's something that you, at least when you see it, I would like you to remember that it's an exponential distribution with a little bit different variable, and the change in the variable is just this alpha that you put in the exponential, okay? And that become a Bible distribution, all right? That would be good that you know. Then you will have two parameters, alpha and lambda. Lambda comes from the exponential distribution, and alpha is a new component from the Bible. And usually you denote it like this. And yeah, we have here again some pictures on how it look like for different k. Here will be alphas. It doesn't let me. Okay, just this picture to be from some other place, but k will be alpha. Okay, so you can see that for lambda equal to 1 and alpha equal to 5, it looks quite normal, but it has some. It's like the Pisa Tower, right? It's like a little bit to the right. And then you have pure, very close to the exponential here when lambda is equal to 1 and alpha equal to 0.4. The expected value is this formula you see here, and the variance is like here. So I say loosely because it doesn't make sense that I speak what it says here, because you're not going to remember, and I don't think you need to remember, but I want you to know that for each distribution there is a cumulative density function, and there is an expected value, and there is a variance, and there is a standard deviation. Okay? And each distribution will have their own parameters. All right. With that, today is over. I think it was I hope easygoing class today. We learned about cumulative density function, the continuous domain of the distribution, and continuous domain of Gaussian distribution, exponential, gamma that contains many other distributions, and Weibull distribution. And with that, thank you, and see you next week.